at this point we've talked about, vaporization, condensation, right? Going from liquid to gas, gas to liquid. We talked about melting, freezing, liquid to solid, solid to liquid. Those are sort of our normal ones. But we also have sublimation. So sometimes things go straight from a solid to a gas. So when we have a substance sublime, we have molecules that leave the surface of the solid, again, where they're held less tightly than the interior, and become gaseous. I think the most relatable example of this is dry ice, which you can go to a grocery store and buy dry ice. It's like $2 a pound, and they usually sell you like $7 or 7 pounds worth, so it's like $15 or so. And you have to handle it correctly, but it's not too dangerous, I should say. You can make some very fun punch for Halloween. It doesn't melt at atmospheric pressure, though, right? So if you buy dry ice, it's just slowly turning to a gas. And after about 24 hours, it's gone. And its temperature is negative 78 degrees C. So at that temperature, the CO2 molecules have enough energy to leave the surface of the dry ice and become gas. Dry ice, though, just does this fast enough that you can see it. All right, so we got solid dry ice, turns into a gas, happens rather quickly at room temperature. Regular ice actually also sublimes at temperatures below 0 degrees C. So in cold climates, which we don't really get snow around here, but ice or snow laying on the ground will just gradually disappear, even if the temperature remains below 0, even if it remains overcast and there's no sunlight shining directly on it. Also in your freezer, ice cubes will slowly become smaller, even though your freezer is always below 0 degrees C. It takes a long time for that to happen, but it happens. And ice also will sublime out of frozen foods. So the ice crystals that form in the bag, that's water that's sublimated out of the food and then redeposited. So deposition is the opposite of sublimation. That ice is then redeposited on the surface of the bag. And that's what causes freezer burn. That any liquid or ice in the freezer will also condense on the cooling coils at the back of the freezer. And that's why every once in a while you need to defrost your freezer, because otherwise the ice just continues and continues and continues to build up there. And it can stop your freezer from working, actually. So if you have a ton of ice built up in the back of your freezer, you should probably defrost it. Makes it less efficient, too. Costs you more in electricity. So if you can get colder and colder temperatures, like deep freezing, you could reduce that sublimation and preserve food longer. Okay. So those are basically changing phases, which is related to intermolecular forces. But intermolecular forces are at the core of all of those processes, right? We talked about why the temperature doesn't change when you're melting something or when you're boiling something. It's because all of the energy goes into overcoming those intermolecular forces. And things boil at different temperatures because of intermolecular forces. So these forces are electrostatic forces of attraction between molecules. The strength of the intermolecular forces determines the state. So something that's a solid is going to have stronger intermolecular forces than something that's a liquid or something that's a gas. Assuming that all things are at the same temperature. Stronger intermolecular forces tend to result in liquids or solids, and weak intermolecular forces tend to result in gases with low melting or boiling points. So the first force that we're going to talk about is also the weakest force, but it's the force that occurs between all things. Actually, I was looking this one up a little earlier. These dispersion forces, are also called London forces or London dispersion forces because they were proposed by Fritz, I think it was Fritz London, way back. Essentially, he proposed these dispersion forces as a reason that molecules like helium or xenon, these noble gases, right, as we talked about, they have full well, actually helium only has two, but something like xenon would have a full valence shell. Doesn't have any charges on it, but if you cool them enough, they will condense into liquids. And so these dispersion forces were how he proposed that they could exist as liquids, right? Because there has to be some force in between them that's causing them to stick together. So these dispersion forces are caused by fluctuations in the electron distribution within molecules or atoms. So, especially for something like xenon, where's my periodic table here? Let's look at the periodic table, right? So it's going to be, in the end, it goes 1, 2, 3, 4, 5. Principal quantum shell. So it's going to have 1, 2, 3, 4, essentially 5 layers of electron shells that are around it. Remember, these are orbitals, so they've got all kinds of different shapes, but generally each one gets larger and larger and larger. And so when you have something like this, it's kind of like, I don't know if you guys have ever done this, but I had much younger siblings, so I had like these, they had like those, little baby stacking cup things, and you could take the middle stacking cup if they were spaced out enough, and you could like slide it around so it could be more on one side or more on the other. That's kind of what's happening here in a sense. So instead of the xenon and the electrons always being perfectly centered on each other, sometimes the electrons can get pushed over to one side. So then the side that has more electrons is going to be slightly negative. The side that has fewer electrons is going to be slightly positive. So the London force, or the dispersion force, is caused by these electrons shifting from side to side around these atoms or molecules that otherwise don't seem like they should be able to stick together. So it's kind of like this picture here. And these are called instantaneous dipoles. So if our helium atom here, these electrons are roughly on either side. Here, they're roughly on either side of the nucleus. Again, this is the nucleus. That's the center of the atom. That's the positive charge. But you might get in an instant where both of the electrons are on the same side. Because, again, I don't know if you remember this, but they can sort of appear and disappear at anywhere randomly within the molecule or within the atom. So when this happens, we get this, which this is a lowercase delta, which means when it's delta negative, that's slightly negative. And delta positive is slightly positive. So these, remember, opposite charges attract. So if we have something that's got a positive charge, it's going to attract things that have negative charges, and vice versa. So you can imagine if you had one helium like this, and it bumped up to another helium atom, this negative charge would also repel these electrons instantaneously, so they'd go to the other side, and you'd end up with a partial positive and a partial negative. So all of these atoms bumping together are causing the electrons in the other atoms to shift around randomly for very momentary dipoles, or instantaneous dipoles. Oh, this is what I was just explaining. So, right, so one instantaneous dipole could induce an instantaneous dipole in another atom, which would induce it in another atom, and so on and so forth. So there's an amount of attraction between all of them, even if it's very small. Because you have to get helium down to like negative 200 and, it's like negative 260 degrees Celsius, 270, before it actually turns into a liquid. So the dispersion force, this is an attractive force, occurs as atoms attract one another, and the positive end of one instantaneous dipole attracts the negative end of another. So the dipoles responsible for the dispersion force are transient, so meaning temporary, constantly appearing and disappearing in response to fluctuations in electron clouds. The magnitude of the dispersion force depends on how easily the electrons in the atom or molecule can polarize in response to an instantaneous dipole. So this is kind of like if you had, I'll try for another analogy here. If you had like small cups of water, just bear with me on this. If you bump one of these cups into another cup, the water in this cup is going to slosh over to one side, and it's going to bump into this one, which is going to cause that to slosh over to the other side. And if you had a bunch of them, they would all kind of do this together. And now they're not going to slosh very far because the cups are small. But if you blow this up to the size of something like a kiddie pool, now when this sloshes all over to one side, it's a lot more water moving, and it's got more space to move in. Similarly, if you have a large electron cloud, that atom is more easily polarized, atom or molecule, for that matter. And this kind of goes back to when we were talking about trends in the periodic table. I always hate that I can't point on this thing, but if we're looking at this periodic table, remember that the top right of the periodic table is the smallest, so fluorine is actually the smallest atom. As we go down each row, we're adding more and more shells of electrons. So to compare something like neon and xenon, xenon is going to have much larger, or essentially a larger pool of electrons to slosh around back and forth. And this trend actually plays out when we look at boiling points. Because remember, the boiling point is dependent on the amount of energy it takes to overcome the intermolecular forces to become a solid or liquid, go from a solid to a liquid or a liquid to a gas. So for helium, its boiling point is 4.2 Kelvin. So that is just above absolute zero. But if we go all the way down to xenon, right, again, which is in the n = 5 principal quantum shell, so it's got a lot of electrons around it and much larger orbitals. That's going to have a boiling point of 165 Kelvin, right, which is 40 times larger than helium's. So when you're comparing similar atoms or similar molecules, molecular weight can tell you which one is going to have a higher boiling point or a lower boiling point. Okay, so we can, I do have a Mentimeter quiz for this one. Flip over to that. Okay, so, and again, this is all on the same quiz, so if you kept that open on your phone, it should either tell you that I've switched to a different slide, or it should automatically switch you there. So you've got these two hydrocarbons, and all a hydrocarbon is, it's a molecule made up of hydrogen and carbon. Yeah, so which of these has the higher boiling point? We already got one response. I'll draw these out too, so you can kind of see them in their skeletal Lewis dot structures. And remember, the one that has the larger pool of electrons is going to have the higher boiling point because it's more easily polarizable. 3 votes so far. Oh, screen's freaking out there. Oh, that's cool. I can switch it between percents and numbers. 75% say it's a C2H6. Got some more votes, 6 votes now. There are only 6 people paying attention. Oh, here, just I'll post this again. So it's on the top there of the slide, which might be too small to read on your computer or phone or whatever. If you go to menti.com and type in this code, it should pop this up and you can vote there. And this is something that we'll use for in-person classes as well. It's completely anonymous. Like, I won't see who said what, but it will help me know if I've explained something well enough, or if I need to go over it or go into more detail, or, you know, ask if anybody has any questions. Cool, cool, cool. 2 and 6. I'll leave that up there so those of you who are still trying to figure it out can get there. But yeah, it is this. It's the larger hydrocarbon. So a molecule like this is going to have, and actually even just drawing a circle around like this is accurate enough, but it's going to have a larger electron cloud. And so those electrons will be able to shift more in response to instantaneous dipoles. So generally speaking, for similar molecules, the larger it is or the heavier it is, the higher the boiling point is going to be, because the intermolecular forces are going to be stronger. Here's the C2H6. Yeah. Because it's larger. Yeah. Mm-hmm. Yeah, and of course, feel free to, like, for anybody else too, feel free to just pop in and ask a question. That's fine. All right. So this is dispersion forces, and we're going to move on now and talk about a stronger intermolecular force. So dispersion force is the weakest one that we're going to talk about. We also have the dipole-dipole force. So dipole-dipole force exists in all polar molecules. This is a bit of a throwback to, remember we did Lewis dot structures, and we talked about Vesper theory. R. And that was where we looked at the number of electron groups. So for something like water, if you draw the Lewis dot structure, we get something like this. And so it has 4 electron groups. I guess I'll just abbreviate that as EG. It has 2 bonding groups, symmetrically 4, and it has 2 lone pairs. And remember that if the central atom has lone pairs, it's going to be polar, and that's because these electrons, these lone pair groups, make this molecule asymmetrical. And so they're going to have a negative charge, while the other side will have a slightly positive charge. So in our dispersion forces, those molecules had temporary dipoles. Those had temporary dipoles. These polar molecules have permanent dipoles. So on water, that's always slightly positive on one side and always slightly negative on the other side. So like magnets, they'll stick together, positive to negative, positive to negative. So, yeah, positive end to negative end. And while all molecules have dispersion forces, polar molecules also have dipole-dipole forces. So they've got both going on. And then because these dipole forces are stronger, they have higher melting and boiling points, if it's a solid or a liquid, relative to non-polar molecules of similar molar mass. And again, whether something's polar or non-polar, until you develop an intuition for it, you'll probably have to do the Lewis dot structures to figure that out. So another polar molecule here is formaldehyde. It has a permanent dipole moment. The positive end of polar molecule is attracted to the negative end of its neighbor, giving rise to the dipole-dipole force. So here, instead of having lone pairs on our atom, we have oxygen and carbon. So this bond is going to be polar, where oxygen is more electronegative than carbon. Excuse me. And then because this molecule is asymmetrical, so here, right, this is the oxygen, and these white ones are the hydrogen. The black is carbon. Right, so it's got like a little red cap. That cap is negative, that oxygen. And so that oxygen can line up with the hydrogen side of formaldehyde, and you've got this negative force, negative charge lining up with the positive charge, snapping together kind of like magnets. The effective polarity on melting point and boiling points for two compounds of similar molar mass is pretty stark. So for formaldehyde, has a molar mass of 30, and then we have ethane, which is another molecule with a mass of about 30, right? So it's 30.1. And if we look at their boiling points, this is maybe, I kind of wish these were written in, let me convert these to Kelvin, actually. Oops. So this is 250, I think it's a little bit easier to, 253.65 Kelvin. And this is 185.15 Kelvin. So the boiling point of formaldehyde, which is polar, all right, so this one's polar, ethane is nonpolar, is much higher than formaldehyde, or than ethane, right? So formaldehyde boils at 253.65 Kelvin, whereas ethane is only 185 Kelvin. So that polarity is adding extra strength to the intermolecular forces, requiring a higher boiling point. And the melting point is also higher than that of ethane. So the polarity of molecules also affects miscibility, which I always read in my mind as mixability. So whether or not you can mix two things together. Because miscibility is the ability of a liquid to mix with another liquid without separating into two phases. So this is like if you added oil and water together in the same cup. You can shake it, and they'll kind of mix, but it'll be really cloudy, and then if you leave it for long enough, it'll separate out into the oil and the water again. So miscibility is where if you mix the two things together, that doesn't happen. So it's kind of like if you simple syrup, or if you have like one of those like squirt bottle mix things, those are miscible liquids. And generally speaking, polar liquids are miscible with other polar liquids, but they are immiscible or not miscible with nonpolar liquids. So like dissolves like. This is why you can't wash dishes, for one thing. You can't wash dishes really without soap, or oily hands or oil stains on clothes without using some kind of surfactant, which we did talk about at the end of one of the chapters. So pentane is, it's C5 H6H12, I think, C5H12. So that's a nonpolar molecule. Will not mix with water, which is kind of what this one's showing. Oil and vinegar and salad dressing separate into distinct layers because the vinegar is a polar molecule. Although it's acetic acid in water, so water is polar. And then oil spills also demonstrate that petroleum and seawater are not miscible because that oil will stay, for the most part, on top of the water, which is why it's especially dangerous for birds or fish that jump up through the water, whales in particular too, that need to surface, because as they go to surface or land on the surface of the water, they get covered in oil. So to determine whether a molecule is polar or not, the book has this thing where it's, determine whether the molecule contains polar bonds, and then determine whether the polar bonds add together to form a net dipole moment. Or again, Mrs. K, I need to change these out. because this is the method I use also. A molecule is nonpolar if both conditions are true. And this is the same as when we did Lewis dot structures in, I believe, chapter 9 or 10. If there are no lone pairs on the central atom, and, so both of these need to be true, right, and the atoms bonded to the central atom are identical or have the same electronegativity. For the purposes of this class, really, whether or not they're identical or not. This works for molecules other than diatomic molecules. Oh, did I make a slide for this one? Oh no, I missed this one. Okay. That's right. I didn't make one of these. So this is determine whether whether or not each molecule has dipole-dipole forces. For the most part, we can just use skeletal structures for these. We don't have to do actually the whole Lewis dot structure. So if we have, this one is carbon tetraiodide, so these are I's. So because this carbon atom has all of the same molecule attached to it, and it doesn't have any lone pairs, that's going to be nonpolar. So no dipole force. So dipole-dipole forces only exist in polar molecules. For this next one, we have carbon. Then our skeletal structure will look like this. So here we do not have the same atom for all of these. We have chlorine on one end. So this one's going to be polar, which means it does have dipole force. And then for this last one, HCl, if you were to do the full Lewis dot structure for this one, you would see that this has lone pairs on it. So because this has these lone pairs and hydrogen doesn't have any lone pairs, and this bond is polar, if you were to look up the electronegativity of hydrogen versus the electronegativity of chlorine, it is a polar molecule. So it does have dipole forces. So ultimately, you just need to determine if it's polar or nonpolar, and you can do that with the Lewis dot structure. A lot of the time, you can do it just from the skeletal structure. Sometimes you will need to fill in the electrons, valence electrons, to see if there are lone pairs on the central atom. Are there any questions about that? I'm going to be putting together a series of, I think they're just going to be on Canvas, actually, online things, but more quizzes that you can take, especially on things like nomenclature, the things that I think are really important from early chapters. Those will be coming. Okay, so now we have dispersion force. And we've talked about dipole force. So dispersion force is the weakest. And then this is stronger than dipole-dipole force. And hydrogen bonding is even stronger than our dipole-dipole force. And it's a special type of intermolecular force. So polar molecules containing hydrogen atoms bonded directly to, and this is the key, directly to fluorine, oxygen, or nitrogen exhibit an additional intermolecular force called a hydrogen bond. And this is a super dipole-dipole force. Because what happens is there's a large electronegativity difference between hydrogen and these three other elements, fluorine, oxygen, and nitrogen. And the small size of these atoms allows neighboring molecules to get very close to each other. So what happens is, if you have hydrogen bound to fluorine, remember, electronegativity is how much an atom will suck electrons away from, well, really suck electrons to itself. How greedy it is with electrons. So fluorine is very electronegative. So to envision these electron clouds, it's almost primarily going to have all of those electrons around fluorine, and most of it not around hydrogen, which means that hydrogen here is fairly positive. Now, if you have another hydrofluoric acid molecule here, and again, all of these electrons are around fluorine, because these atoms are really small, this negative charge, this would have a negative charge too, this would be a positive charge, is able to get really, really close to hydrogen. And it essentially forms like a pseudo bond with that other hydrogen. It's still much, much weaker than an actual bond inside of a molecule. So hydrogen bonds occur between separate molecules. It's an intermolecular force, so it's going between two different molecules. Covalent bonds occur between atoms within the same molecule. So covalent is within the same molecule. And even though hydrogen bonds are very strong, they're still only 2 to 5% the strength of a typical covalent bond. Right, so 50 to 20 times stronger. Covalent bonds are 50 to 20 times stronger than a hydrogen bond. But, so let me do this actually. So we've got our dispersion force. Dispersion, so if we're talking strength here, this is weak, this is strong. We have dispersion force, then we have dipole, then we have hydrogen. Maybe I should draw a line here, I don't know. Covalent is all the way over here. So hydrogen bonds are much stronger than dispersion forces. They're stronger than dipole forces, but they're still much, much weaker than a covalent bond or covalent force. So kind of like the example that I drew out earlier, you can get hydrofluoric acid molecules lined up like this. The hydrogen on each molecule is strongly attracted to the fluorine on its neighbor, forming like a conga line. The intermolecular attraction of a hydrogen atom to an electronegative atom, this is what we call the hydrogen bond. So hydrogen bonds can occur between fluorine. They can also occur between hydrogens directly attached to oxygen atoms. So in methanol, and I can draw, let me draw this out too. So we got C, and there's hydrogen, and then this oxygen has a hydrogen on it. So that's what we're seeing in these. We've got hydrogen atoms directly bonded to oxygen. So then these methanol molecules can hydrogen bond to each other through this oxygen, hydrogen, oxygen, hydrogen, and then there'd be another, oxygen, hydrogen, methanol molecule over here. So the hydrogen atom on each methanol molecule is attracted to the oxygen atom of its neighbor. So we can see this again, how it affects melting and boiling points. For methanol, which has a mass of 30 grams per mole, molar mass of 30 grams per mole, compared to ethane, which is also, 32 to 30, right? So they're really about the same. The boiling point of methanol is 64 degrees Celsius, where the boiling point of ethane is negative 88 degrees Celsius. And that's purely due to this hydrogen bonding effect, and as well as some other dipole-dipole forces. So methanol has dipole, it has hydrogen bonding, it also has dispersion. Forces, whereas ethane just has dispersion forces. So in addition to like dipole forces and hydrogen bonding forces being stronger than dispersion forces, they also kind of have an additive effect, right? It's kind of like, I don't know, drinking different types of caffeine. Like if you wake up in the morning, you have a cup of coffee, and then you go and you have, you know, a Mountain Dew, and then you follow that up with a Monster. Even though those are all different types of caffeine source, and they are different strengths of caffeine sources, they're all going to put more caffeine in your body and thereby make you more, I don't know, either productive or just have an anxiety attack, depending on how you respond to caffeine. So we can add these forces up, and the more of them we have, the stronger the intermolecular forces, and then the higher the boiling point or the melting point is going to be. Water also has hydrogen bonding because, again, we have hydrogens directly attached to oxygens. So that's one of the qualifications for hydrogen bonding. But each water molecule has two hydrogens directly attached to the oxygen. So it can actually form two hydrogen bonds, which is why the boiling point of water is 100 degrees C, even though it's only 18.02 grams per mole. So smaller than, we can go back to this, it's much smaller than, half the size almost, of methanol, yet it has a higher boiling point than methanol. So it basically has the dispersion force, because everything has dispersion forces. It has dipole-dipole, and then it has hydrogen, but it has hydrogen bonding times 2. All right, so it doubles that effect. Again, this is like having, you know, a coffee. I guess depends on if your coffee is, I don't know if your coffee is weaker or stronger than Mountain Dew. You know, you're having a coffee, you have Coke, and then you have 2 Rock Stars, or Bang, or whatever energy drink you like. So its boiling point is even higher than because of that. And the 2 strands of DNA are actually held together by hydrogen bonds. Right, so it's between the different base pairs have these, I'll zoom in on this, right? This is a hydrogen directly attached to nitrogen there. Hydrogen attached to nitrogen, so they can form hydrogen bonds with the other base pairs, and that keeps it together. I think I'm going to make it. Aha, I did have a slide for this one. A Mentimeter slide. Okay, so, and maybe we'll all, I didn't make more slides for this. I should have made more slides. Let me switch to that. Okay, so we're going back to the Mentimeter quiz. Again, you should be able to just leave this open. And it should switch along with the presentation. I'm not sure how that works exactly. Or it'll tell you that I've switched to a different slide. So here we're looking at which one has the higher boiling point. HF or HCl. So you got to think about the 3 different types of forces that we've talked about so far. Dispersion, dipole-dipole, and hydrogen bonding. And so far we've got 6 votes for HCl. Are we going to get any more? 7? 8? All right, all right. A verbal vote for HCl. Is anybody going to buck the trend? I realize I don't have my camera on this slide, on this scene. One for hydrogen fluoride. See if I can. It doesn't look like that worked. Okay, so let's talk about this then, because I can see why you would vote for HCl. HCl is larger, right? So you change your... Okay. Do I have any... What controls do I have here? I don't know if I can, like, actually... Oh, show voting instructions. Oh, that's that. I guess I could reset the results if people wanted to change it. I'll try and figure out if there's a way that I can have people, like, let you guys change your votes if you want to. But let's go through and look at these. So both of these are polar. So first off, both are going to have dispersion forces. And both of them are polar, so they're both going to have dipole forces as well. And actually, we can look at this, and so the dispersion forces of HCl, and I think this is why most people picked HCl, is going to have larger dispersion forces. I think the dipole forces might favor hydrogen fluoride here, actually, although I think for the sake of this, we're going to say that they're about equal. But hydrogen fluoride has hydrogen bonding as well. And HCl does not have hydrogen bonding. So it means that hydrogen fluoride actually has the higher boiling point. So you just got to remember, and I definitely understand why you guys voted for HCl, because it's larger. But if you have hydrogen directly bound to nitrogen, oxygen, or fluorine, that's going to have hydrogen bonding, and that's going to have the stronger intermolecular force, and therefore the higher boiling point. Yeah, so what do you mean what's always? That hydrogen directly bound to nitrogen, oxygen, or fluorine? Will always be stronger. If you're comparing it to something that doesn't have a hydrogen bond. So HCl doesn't form a hydrogen bond intermolecular force. So essentially you could look at this as like who's going to be more, if we're going back to my silly caffeine analogy, you know, who's going to be more hyped up on caffeine? It's going to be the person who had the coffee, the Monster, or sorry, not the Monster, the Mountain Dew and the Monster versus the person who just had coffee and a Mountain Dew. So those things add on top of each other. Okay, so now going one step higher than our hydrogen bond, we also have ion-dipole forces. So these ion-dipole forces occur in mixtures of ionic compounds and polar compounds. So it's especially important for aqueous solutions of ionic compounds. So this would be, remember, aqueous solution means something dissolved in water. So sodium chloride, right, table salt, dissolved in water, would have ion-dipole forces. So when sodium chloride dissolves in water, the negative chloride ions interact with the positive poles of water molecules, and the positive sodium ions interact with the negative poles of the water molecules. And so that's what you get here, right? So the hydrogen side of the water is positive, so those surround the negative charge of the chlorine. And the oxygen side of the water is negative, so those surround the positive charge of the sodium. So here's this nice summary table for you. We have dispersion or London forces. That's the weakest, but does increase with molecular mass. We have dipole force, which is going to be moderate, hydrogen bond, which is strong, and then our ion-dipole force, which is very strong. So that's the highest. So really, like, this is the kind of question that I would ask on an exam. You know, either give you two things and ask you which has the higher boiling point, or to rank these forces in order of increasing or decreasing strength. So really the important things to, I mean, this table sort of summarizes everything that we've just covered, and really the important points about it, so that you can look at a type of molecule, determine if it's, you know, nonpolar, if it's polar, if it has the potential for hydrogen bonding, so if it's got fluorine, oxygen, and nitrogen, and then if it's a mixture, and then being able to rank those forces. So changing gears a little bit here, and we talked about solids way, way back, you know, different types of solids, that the fact that there are crystalline solids, and amorphous solids, right, where the crystalline solids have a well-ordered array of atoms or molecules, and our amorphous solids have no long-range order. Our crystalline solids can be divided into three different categories, actually, based on the individual units that compose the solid. We have molecular crystalline solids, ionic crystalline solids, or atomic crystalline solids. And we have different naming schemes for ionic or molecular solids, if you remember from the beginning of the class, chapter 5. So you put these into a nice little flowchart. And the key differences between these are this yellow row here. So molecular solids have composite units that are molecules. So they're sort of independent entities of atoms bound together. So something like ice, right? So that's made up of individual units of H2O. We have ionic solids, where the component units are formula units of cations and anions. There's not a lot of room here, but that's like sodium chloride. So remember that sodium chloride is actually a lattice of, and I brought it to class once, that model. It's a bunch of sodiums and chlorides all stuck together based on the positive and negative charge of the sodium and the chlorine. So when we write out NaCl, we're just writing out the simplest unit of that lattice or that grid. Then our atomic solids, the smallest unit of those is the individual atoms. And those are usually going to be, well, actually, I won't just say usually, those are always going to be pure elements, because the entire thing is composed of just a single type of element. I guess amalgams might change that a little bit, but we don't talk about those. Molecular solids are solids whose composite units are molecules again, so something like ice or dry ice, which is made of CO2. They're held together by intermolecular forces that we just covered, dispersion, dipole-dipole forces, and hydrogen bonding. Ice in particular is held together by hydrogen bonds, whereas dry ice is just held together with dispersion forces. And they tend to have low to moderately low melting points. So ice, we know, melts at 0 degrees C. Dry ice doesn't melt, but it sublimes at negative 78 degrees C. So they tend to only exist as solids at cold temperatures, is essentially what this is saying. I'm going to put cold in quotes here, because it's all kind of relative. Ionic solids, on the other hand, are solids composed of formula units, again, like table salt, sodium chloride, or calcium fluoride. I have a little more room here, so I can draw this out again. So kind of like the sodium, chlorine, chlorine, right? It's a grid. a repeating pattern of these sodium and chloride atoms. Something like calcium fluoride is going to be a little bit different in that there's going to be a calcium and then fluorine. I actually don't know what this would look like. Maybe it's like this. Sure, let's do it like this. So for every calcium, there's 2 fluorines. So these are actually held together by electrostatic attractions between cations and anions. So we talked about like our dipole-dipole forces existing as partial positives or partial negatives. And, you know, those were stronger than dispersion forces, which are even weaker, positive and negative charges. Here we have true full-on ions. So the calcium is going to have a +2 charge, a full formal +2 charge, and each fluorine is going to have a full negative charge. Not a partial, not a slight charge, but a full charge. So those electrostatic attractions are stronger than the intermolecular forces that we talked about. And they have high melting points because these bonds are strong. So sodium chloride melts at 801 degrees Celsius. So they exist as solids at, you know, up to very high temperatures. The last type of solid, crystalline solid, that we're going to talk about here are the atomic solids, whose composite units are individual atoms. So things like diamond or iron or solid xenon, if you get it cold enough. Atomic solids can be divided into 3 categories, each held to a different kind of force, and their melting points vary widely. So diamond is going to have a higher melting point than iron, is going to have a higher melting point than xenon. So this is, again, our 3 different types of atomic solids. I think we'll get a tree here at some point that's going to include those. But you can essentially take the flow chart from before, where we had the types of crystalline solids, which was the first? Molecular, this one, right? So we've got our molecular solids, ionic solids, which we talked about, and then now we're talking about atomic solids, and this can be further broken up into 3 categories. And that's what we're seeing here. So we have covalent atomic solids. Silicon is one of them, but diamond, which is solid carbon, where the individual atoms are actually held together by covalent bonds. And remember, covalent bonds are where the atoms are sharing electrons. We have non-bonding solids, atomic solids, which are just held together by dispersion forces. So this is xenon in particular, was the one that Fritz Haber, different story, Fritz London, that's why he came up with dispersion forces, was to explain why something like xenon could exist as a solid or as a liquid. And then we also have metallic atomic solids. So things like gold, things that are made of metals. And again, these are covalent solids are going to have high melting points. Atomic solids are going to have low melting points. Metallic solids have variable melting points because metallic bonds are weird, if I'm being perfectly honest. And I do want to point to this fact again that our covalent solids, atomic solids, right? Covalent atomic solids are held together by covalent bonds. These covalent bonds are much, much stronger than any of the intermolecular forces that we talked about earlier, which is why they have high melting points. Non-bonding atomic solids are held together just by dispersion forces, which are the weakest of the forces that we've talked about today. So they have low melting points. I mean, like really low melting points. So keep that in mind, that like the strength of the different types of bonds explains all of these other things. It's kind of the difference between law and theory. So our covalent atomic solids, again, are held together by covalent bonds. Diamond is one example. So each carbon atom in that diamond structure is going to be forming 4 covalent bonds to 4 other carbon atoms, and each of those carbon atoms will have 4 covalent bonds. And they form a tetrahedral geometry. So you can actually, and I think this is really, really cool, a single diamond crystal can be thought of as a single molecule. All of those atoms in there are all covalently bound together, so that is one molecule. The melting point is very high because these are strong bonds. It's like 3,800 degrees C. As a side note, if you're looking at like, diamond purities or diamond ratings and stuff, any of those, any coloration or any of the, I think they even call them occlusions, are from other materials that aren't carbon. So things that are breaking up that repeating diamond structure or repeating diamond pattern. So this is an example of just one piece of what would be this entire diamond's structure. And it forms a 3-dimensional hexagonal pattern, which is kind of hard to see here. So there's 1, 2, 3, 4, 5, 6 sides of one hexagon. And then if you can follow this, there's 1, 2, 3, 4, 5, 6 sides there too, sort of going up and down. So it's all these repeating hexagons. Very, very, very stable. Non-bonding atomic solids are held together by relatively weak dispersion forces. So xenon atoms have a stable electron configuration because they're a noble gas, right? So they've got 8 valence electrons, very stable. Because of that, they don't form covalent bonds with each other. And their melting point is negative 112 degrees C. So diamond melted at 3,800 degrees C. This melts at negative 112 degrees C. Quite a bit different. Metallic atomic solids are held together by metallic bonds, which in the simplest model is a positively charged ions in a sea of electrons. And this varies drastically, where mercury melts below room temperature of negative 39 degrees C. Iron melts at 1,809 degrees C. And then I think tungsten has a melting point of like 6,000 degrees C. So they're all over the place. And this is where the d orbitals are sort of getting messy. So this is kind of what it's like. We have these positive metal atom nuclei in a electron sea. So depending on those metal atoms and those electrons, that's why we get so many different melting points. Oh good, I did have a slide for this one too. And this one's a little bit different, so we're going to try this out. So we go back to Mentimeter. I can actually make this larger, huh? Okay, so we're going to have here identify each solid as molecular, ionic, or atomic. And so for this one on your phone, you're going to have a slider. Oh, I just saw this text message. I see that you're in, or I thought I saw just some, how is it? Yeah, I will post this recording, by the way. Okay, so yeah, you can move each slider for these. 0 is going to be molecular, 1 is going to be ionic. So 0 is molecular, 1 is ionic, and 2 is atomic for each of these on the Mentimeter quiz, or Mentimeter slide. Oh, yeah, I still have it pulled up here. So part of this you can use, actually I would say you can use what you know, hopefully what you know about nomenclature to figure out if these are molecular, ionic, or atomic, because it's the same rules. Those nomenclature rules that we use to name molecular solids were for molecular solids, which are the same as what we're describing here, these crystalline molecular solids. And then ionic compounds, we learned the naming scheme for ionic compounds and how to identify those. Hey, we got one vote in. Cool. This one's kind of fun because it kind of, I mean, if I click on, will it, no. So by voting, you guys can move the sliders slightly in either direction. Oh, I see. And if I hover it, it tells me exactly how much they were voted for. Fairly split on these. You do have to hit, I think, submit at the bottom for it to actually go through. For the sake of time, though, I'll keep going. Because we're almost done with this. We're just going to talk about water for a couple slides afterwards. Ooh. Had one vote for molecular on Krypton. Yeah, so identifying these as molecular, ionic, or atomic, really, we've talked about sort of like the concept of what makes them molecular, ionic, or atomic in these slides today. But the identification for which type is the same as when we did nomenclature. So for molecular solids, you need to look at it and say, okay, are there any metals? So if we're looking at NH3, we don't have any metals there. And this is a molecule that we've been given. I know that's a little bit rough to think of it maybe that way as a molecule, but we're given a molecule here. So this is a molecular solid. And I guess the thing that distinguishes it from being an atomic solid is that it's made up of more than one type of atom. So an atomic solid is only going to be made up of one type of atom. For a second one, again, we identify first, are there any metals? And here we do have a metal. This is calcium. And it's bound to a nonmetal, which is oxygen. So it's going to be ionic. And then as I mentioned with the first one, here we only have a single type of atom. So that is going to be an atomic solid. And this is where I think I've suggested this in the past, is try making a decision tree for yourself for how to identify these types of things. So if we're looking at these three especially, what is different about the atomic solid versus an ionic or molecular solid? Well, this only has one type of atom. And then you can kind of try a few more examples and see if that applies more universally. And I'll tell you that it does. If you have one type of atom and you're told that it's a solid, then that is an atomic solid. So your first question could be, is there more than one type, or I should just say, I could say just more than one element? Right? If the answer to that is yes, that's an atomic solid. If the answer is no, okay, that doesn't, answer our question yet, but it leads us to another question. Is there... Oh, I do have that backwards. You're right. Sorry. Is there more than one type of element? If there's not more than one type of element, then it's an atomic solid. Yeah, sorry about that. I blame COVID. Okay, sorry. Yes. If there is there more than one element? The answer is no, then it's an atomic solid. If there is more than one element, yes, then the next question you can ask is there a metal? Because molecular solids don't have metals. So is there a metal? No. Then that's molecular. If the answer is yes, then it's going to be ionic. I don't know why I keep trying to write I twice. So these kinds of decision trees can really, if you can put this kind of thing together, then you have a good enough grasp of the thing that when you get it on a test, you'll be able to sort these things out into their respective categories. All right. Moving on, though. We're going to talk about water. So water is a fairly special molecule. A lot of the reason is because of the hydrogen bonding, right? Again, we talked, it can basically do 2 hydrogen bonds per water molecule. So water has a low molar mass, 18.02, yet it's a liquid at room temperature instead of a gas. If we look at these other sort of similarly structured molecules, H2S, H2SE, so hydrogen selenide or hydrogen telluride. These all have boiling points below 0 degrees Celsius, whereas water boils at 100 degrees Celsius. So part of that is, or well, that in this case is due to the hydrogen bonding compared to those other molecules. Water is also very polar, which allows it to dissolve many other polar and ionic compounds, so things like salt or other types of salts, so not just sodium chloride, but like magnesium chloride, for example. And it's the main solvent of living organisms, so our bodies use it to transport those salts. Things like calcium or potassium are super important for, muscle contractions, right? Like your heart is a muscle that needs those salts to contract, as well as the other nutrients that are transported, like sugars throughout the body. So life is impossible without water, and in most places on Earth where liquid water exists, life exists. Which is also why if you leave, water like in anything for too long, like mold starts growing. That just happens. Unfortunately, speaking from experience there. So where life exists, water exists because it makes life possible. So this is why, if you've heard reports of evidence of water on Mars, which there is water on Mars, it's mostly ice, but liquid water in particular has fueled hopes of finding life on Mars. Speaking of other space stuff, sorry, I know it's 6:30 now. Europa is one of the places where scientists think that life might exist because it's got a frozen crust, but the inside of Europa is mostly liquid water, which is caused by the gravity of Jupiter. Europa is one of Jupiter's moons. Gravity of Jupiter actually heats the inside of Europa and keeps that liquid. So life might exist there, which would be pretty neat. Water freezes also in a unique way. Most things, when they freeze, contract and get smaller, which makes them more dense. Instead, water, when it freezes, expands, which is why if you've ever put a soda can in the freezer, it sometimes explodes, sometimes just bulges out crazily. That's because the water expands. So ice cubes and icebergs float, but also the frozen layer of ice at the surface of a lake insulates the water of the lake from further freezing. So then other aquatic life in the lake can continue to live even though the surface is frozen. This is also the reason why many things do not survive. Most organisms do not survive freezing. Anything larger than a hamster. Actually, here's a fun side story. Microwave ovens, the technology used in those, was invented for thawing frozen hamsters. Because they were trying to test like cryosleep. Can we freeze humans eventually? And like you could live frozen, or I guess be suspended in stasis, frozen, and then be thawed out later, 1,000 years in the future or whatever, kind of like Futurama. But they were testing this with hamsters, and they found that using microwave radiation, you could more evenly thaw out the hamsters, and they would survive freezing more often. They also found that anything larger than a hamster doesn't work. All right, sorry. So that ends chapter 12.